Oh, hello there. Today on Real Chem, we're gonna dive into the unseeable world of acid-base indicators. You might be asking yourself, what do banjos and acid-base indicators have to do with each other? Well, grab your goggles and your tuning fork, because the answer is all about frequencies. Here, we have 6 seemingly unremarkable beakers, but hidden within them lies the potential for a rainbow connection, if you will. These beakers each contain a little acid-alcohol mixture and just a pinch of different pH indicators, chemicals that change color based on the hydronium ion concentration of their environment. But to unleash their colorful potentials, we'll need to add a dilute sodium hydroxide solution, our base. But first, let's talk about how this works. Let's take phenolphthalein as an example. In its acidic form, it's colorless. Why?
Because the molecule has lots of localized electrons confined to smaller areas.
A smaller area means a higher energy gap, so it absorbs light outside of the visible range. But when we add a base, the molecule gets depronated. This changes the structure of the indicator because the molecule has lots of delocalized electrons that can roam all over a big area. This delocalization lowers the energy gap between the molecule's electronic state. So the molecule now absorbs and reflects light in the visible range, giving us that bright red color. It's just like a banjo string. You shorten the string, and the sound frequency increases. In molecules, shortening delocalization increases the frequency of light they can absorb. This is where the Henderson-Hasselbalch equation comes in. It tells us the relationship between pH, the pKa of the indicator, and the ratio of its protonated and deprotonated forms. When the pH equals the pKa, you'll get a mix of both forms. And often, that's the midpoint of the color change for an indicator. I can switch the color back and forth by adding acid and base, thus changing the ratio in the Henderson-Hasselbalch equation. It's like moving up and down the neck of the banjo. Now, let's bring this rainbow to life. As I add the base, the pH increases, deprotonating all of the indicators, revealing their true colors. Red, thanks to a mix of phenolphthalein and p-nitrophenol. Orange, just a little different balance between the two indicators. Yellow, pure p-nitrophenol. Green, a delicate dance between thymolphthalein and p-nitrophenol. Blue, thymolphthalein, taking center stage. And finally, violet. A symphony of phenolphthalein and thymolphthalein. And there you have it, a complete rainbow, all thanks to the chemistry of acids and bases, coupled to delocalized electrons. In general, when you choose an indicator, you want its weak acid pKa to overlap with the endpoint of the pH of the acid or base you are titrating. This may sound like an insane task, but oftentimes you can find an appropriate indicator using a chart like this one. But what happens when we reverse this process? Let's find out. This jar contains an acid that's about to steal the spotlight. The acid reintroduces protons, putting the molecules back in their protonated, colorless form.
It's like caging up the electrons. This increases the energy gap and shifts the absorption back out of the visible range.
Just like that, the rainbow disappears. The pH is now low. The indicators are protonated. So, what do pH indicators and banjos have in common? Well, Both let us explore the world of frequencies, whether it's sound waves from a string or light waves reflected by molecules. And that's real chem.